Okay, so hello everyone. Uh, uh, shall we start now? Mm. So, do you have any questions about the last lectures about the problems? Mm. Ah. Hmm? Ah. Mhm. Yeah. Concerning the exam, I've asked how this should be organized, and it will look like follows. There will be a written exam where I'll give some number of problems, like three, maybe more, very similar for the problems in this list, which I'm updating. So you need to solve them in some reasonable amount of time, and then there will be our part of exam where you will be able to explain what you wrote in the written part, and I will also ask some theoretical questions. So, that, uh, no, mostly about the course. Like if you know, and if you want to tell about some physical intuition, physical explanation, it would be good. If no, then no problem. So the main thing one should know is what to do with the equation once you see it. Like to understand which problems can be formulated for this equation, and how to solve these problems. Like how to write a solution, and when it exists. Uh, so. Um, uh, yes. So does it sound fine? Uh, hmm? Maybe something like a week or more, because I will need to check the solutions, and uh, probably it can be on different days, because if everyone comes on one day, uh, might be complicated, or maybe you can decide that some people come earlier, some later. So we'll find this out. Mm-hmm. Uh, Yes, I will change some numbers. Maybe if the equations, if approaches are similar, I don't remember if there is such an option, but sometimes I can change wave equation to Laplace equation if they can be solved by similar approach. So, mm, so. Mm, mhm. Mm. Yeah. Oh, I forgot. What is the 11 and 12? Mm-hmm. And the integral. Ah, uh, okay. Actually, uh, I need to think. Maybe I will remove some problems which are too computationally complicated, or maybe I will mark them with stars. So. Yeah. Ah. Mm. Mhm. 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 Yeah. Mhm. Mm. Ah. Mhm. Ah. Mhm. Ah. Yes. Well, actually, I think that these problems, well, for example, the problem about gain function 5 dimensions can be solved. So the idea was just to substitute it into the radial part of Laplace equation and solve it. And it should be more or less easy. Ah. But and this can be done easily by comparing to the green function of the Laplace operator, because we can neglect this second term with m squared around 0. So we should compare the leading singularities of two green functions, and they should coincide. Okay. Yeah. concerning the other integrals, so in principle there can be some advanced techniques, but for example, um, we were forced to compute such integrals using only standard techniques like differentiation, integration by parts, and uh, like without any complex analysis. And in principle, it is doable, but well, probably I will not include that problem which might include this kind of traits. So maybe I'll mark them with stars. And after I do this, please tell if it is fine or something else also looks too complicated. Mhm. Uh, yes, thanks for telling this. Uh, uh, okay, so uh, 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 I wanted to tell uh, Mm, it's a good question. First problem is that I missed the first week because of the conference. So it is tomorrow lectures, and then a little bit unexpected problem that one Thursday probably was missing because of holidays. So um, it looks like we need three extra lectures. And there's a question for you. So, is it okay if we organized a kind of 4 hours lectures instead of 2 hours at the end of this semester, or you have something after this lecture? Mm. Yes. Mm, yes. Uh, uh, hmm? Yes. So, well, I think we should have at least one such lecture or some lecture on Zoom on some other day because of this holiday on Thursday. And because we have two lectures, we have two possible lectures after the New Year. So, mhm, 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 mhm. Maybe maybe for me it would be also a little bit better to finish before Christmas. So uh, I also write an email, but probably everyone is here, right? So. Uh, ah, mhm. So I also write an email. I also write about the exam so that it is fixed somewhere. Mm. Okay, so let us go back to the wave equation. Right? Uh, so, so what I was going to tell. Um, ah, so I forgot to tell one nice remark. Well, or not forgot, but don't have enough time. So hmm, at the moment it is in 1+1. One is time dimension, one is space dimension. If I remember we had this problem with a boundary value that if u of 0 x equals to 0, so uh, u t minus u x equals 0 for x greater than 0, t greater than 0. So we have this wave equation on a half line, which starts at some fixed at some fixed time. We also have boundary condition. U of t 0 equals to some v of t. And the solution of this equation was given by the formula u of t and x is v of what of t minus x, right? So v for t v of t equals to 0 for t less than 0. It's just by definition. So we have this solution, and namely this remark. That dt of u of t 0 equals to minus dx of u of t 0. So it means that if we now consider the following problem, that we have a particle of mass m with some force acting on this particle. So let us consider some pole placed at 0. So we have maybe some ring of mass m, and we have a string attached to this ring. Now the motion of this ring is satisfied by the second Newton's law, namely, and we have some external force applied to this ring. Second Newton's law tells that mx with two dots, or maybe m dx squared over dt. squared equals to f plus plus the force acting from the side of this string, and it is given by a tension of this string times times this sine of this small angle, but this sine is just equal to x derivative of u at 0. So so it is kind of this angle is dxu of t0, this angle, and the force of tension is applied here. So this is the y projection of this force, and so we have this equation, but maybe I wrote x. It is better to write v. V is a deviation of this particle. It's v. And now, if we look at this equation, so it tells that u of t0 is actually v by this condition. So it means that it is a dt of v of t, which is a full derivative. So you see that this equation is dv squared over dv d2 squared over dt squared plus this tension dv over dt equals to f. Like this equation, and this this is called viscous friction. So this is some force proportional to the speed of particle and having the opposite direction. The point is that this kind of dissipation with such a force can be modeled by attachment of the infinitely long string. And this trick is used, for example, in quantum mechanics, because equations of quantum mechanics conserve conserve energy. So if you want to describe dissipation, we can add such infinite system which will drain energy of this particle. And it's called Calder-Leggett model in quantum mechanics, but the point is that it is in kind of a nice separation of two equations. One is motion of this particle, and another is equation for the string. So, so. There are Also the other properties of this problem, namely uh, uh, there is such a thing as energy. Mm. So in this case, let us consider this equation on a segment. So u t t minus u x x equals to 0. Uh, and so x is from x is from 0 to L. And we have some initial conditions like u of 0x equals to u0 of x, u t of 0 and x equals to u1 of x. Uh, and let us consider the following object. E of t equals to the integral from 0 to L. So I have not specified the boundary conditions yet, but we will come back to this later when we see what we actually need. So let us consider the following object: ut squared plus ux squared dx. And let us compute time derivative of this. dt e of t is the integral from 0 to L to maybe it's better to insert this 1/2 from the very beginning because of the actual energy. So it is u t u t t plus ux utx dx, right? So now let us use the wave equation here. And you see that let us use it to replace this this tt derivative. It will be integral from 0 to L ut u x x x plus ux u tx. So you might see the total derivative of some function. And what is this function? Yeah, thank you. So it is to go from 0 to L, dx u ut times ux dx. Mm, so it is the it is this difference u t ux from 0 to L. Mm. And so let us continue this blackboard. So dt e of t equals ut ux from 0 to L, and now let us well, so we see that if u of uh, so if u of tx equals u of t0 equals to 0, then mm, this ut equals to 0 of so if u of ux of t0 equals to 0, then well, it's just trivial. It's the same for L, and so uh, uh, if we have Neumann and Dirichlet boundary conditions on each of these ends of a string, and then this energy is conserved. Uh, but I told you that there are more complicated boundary conditions which involve derivatives with which involve some linear combination of u and ux. So if now uh, let us say that u t is given by oh, u x is given by some ux of t0 equals to alpha 0 times u of t0, and uh,
So we showed this for 0. You said that for L it is the same, but we mean that at the same time the condition holds both for 0 and L.
Yes, I'm saying that if these boundary conditions, so we can choose either directly or non-boundary condition on the left and directly or non-boundary condition on the right independently, and both these terms just vanish.
One condition on zero and the other one independently.
Yes. Yeah, so we have four options. By the way, and there are also periodic boundary conditions. It's one option. Another option is periodic boundary conditions. Mm. If you say that u of uh, t L equals to u of t0 and ux of tl is u of t0, then it will mean it means that our string is on a circle. It's a good question how to organize the finite tension, but well, it's possible. Uh, not a problem. So in this case, this dt of energy will be zero just because this value coincides on both boundaries.
The second equation has ux.
Yeah, thank you. Mhm. Yes. So and we have this boundary condition with some other TL equals to alpha L u of L0. Then we see that dt of e of t equals to well, that's fine. Alpha 0 u t of t0 u of t0 plus alpha l u t of tl u of tl. And as a consequence, we can introduce the new object, call it e tilde of t, which equals to e of t minus alpha 0 over 2 u of t0 squared minus alpha l over 2. Actually, maybe I would like to change the sign here. So
The second one, the second condition is half. No, half. When you wrote if ux is 0 is minus alpha 0 ut 0, and the second one is minus alpha yeah,
yeah, thank you. Yes. Mm-hmm. Mm-hmm. Thanks. Alpha L u of TL squared. Uh, so if you introduce this object, then it will be third with time. Hmm? Uh, which one? Yeah. No, I put here R. Sorry, yes. You are right. I should have put a different sign here, and then this sign will be no. Actually, uh, actually the signs should be opposite. It is this one because it's a lower limit, and it is the upper limit. So if I put the signs like this, then it is fine. Oh, I put this signs because I want this to look like energy of harmonic oscillators with uh, this coefficient equal to alpha 0 and alpha L. So I want them to be positive. Mm. So, and this fits this physical intuition that such boundary conditions correspond to uh, springs attached to the end of our string. So we have a linear force here, and these corrections are precisely the energies of these springs. Hmm? Mm-hmm. Yes. Mm.
Can you please repeat this last part of the was lost? So we define a new energy in eta,
Yes.
and that one is a constant.
Uh,
Yeah.
yes.
Okay.
This is because these terms are written here are just uh, derivative, and this is minus dt of uh, alpha 0 over 2 u of t 0 squared plus alpha L over 2 u t L squared. Mm. Is that fine? Mm. So, mm, so we see that uh, we see that the full energy is conserved. Uh, so mm, maybe I should make some make some more remark. Mm.
So this implies uniqueness of solution.
Uh, no, uniqueness of uh, let me think. If you want to prove uniqueness,
Because the energy is in some sense just the the norm, the L2 norm of the gradient.
yes.
So
So,
if we have two solutions, the difference is the solution of the completely homogeneous equation.
yes, yes. Thank you. So it will have uh, so if we have original boundary conditions or if we have initial conditions u equals 0 and ut equals 0, then of course energy is conserved and then the solution should necessarily be 0 for all other times. Yes, thank you. Also also for this boundary conditions. Yes. Mm. So And actually, mm, uh, I'm not quite sure what happens if we put here negative constants. It will correspond to kind of string with negative energy. The situation is a bit unphysical, and I'm afraid that there can be instabilities, like solutions like non like some non-unique solutions can probably appear, but I'm not quite sure. I didn't think about this. So maybe I will think, and if it is something simple, maybe I can answer this problem. Uh, so one. Ah, Also another remark about this mixed boundary conditions. Uh, so we can call it self-adjointness mm, of a second derivative or minus second derivative, mm, maybe d2 over dx squared. So we want we can define a scalar product of two functions by uh, just their integral from 0 to L. 0 to L, f of x, g of x, dx. Um, so it depends on what we want. We can conjugate this function. We can leave it as is. It will not matter for this operator because it is real. So let us just let us consider just this product, and we want it to be self-adjoint. Mm. We want that f 2 primes g equals to f g 2 primes. So it seems that so and this condition is almost satisfied because we can integrate by parts twice, but we should do this carefully because uh, some boundary terms like this can appear. So g, and this is integral from 0 to L f2 primes g dx. It equals to the equal to f prime g minus integral from 0 to L f prime g prime dx from 0 to L, and it equals to uh, to what f prime g minus f g prime from 0 to L. Plus integral from 0 to L f g 2 primes dx. So if you look at this, then this is just the right hand side. It is the product of f with the g 2 primes. And if you want this operator to be self-adjoint, we want to cancel this part. So So we want uh, f prime g minus f g prime uh, from 0 to L equal to 0. And we see that the possible options to achieve this are the following. So, 1. We can say that we actually live on a circle. So, uh, f of uh, f of 0 equals to f of L, g of 0 equals to g of L, and the same for the derivatives, right? So and another option is to say that uh, uh, to say to say that this f and g satisfy such kind of mixed boundary conditions, uh, like alpha um, alpha 0 f of 0 plus or maybe put beta 0 f of 0 plus alpha 0 f prime of 0 equals to 0. And the same for g. Like the same here, there's this condition for also for the derivative. Uh, g of 0 plus alpha 0 g prime of 0 equals to 0. One condition, and the same for L. So if you have this, then we can just replace f prime by f with some coefficient g prime by g, or vice versa, and these two terms cancel. So, so the point is that these mixed boundary conditions are also distinguished by the fact that if you impose them, then this operator of second derivative will be self-adjoint on a segment from 0 to L. So, so is it fine? Uh, so one more thing to know about uh, this equation. By the way, no, let me first do this. Ah, by the way, speaking of conservation of energy, So we see that when we checked that energy is conserved, we differentiated this expression, then transformed a little bit and realized that we have to integrate this by parts. But we can look more carefully at this expression and notice. So it's another remark. Uh, uh, well, here in principle, um, we can say that we don't care because uh, in principle we can solve this equation without this. But it is nice to have this property because in this case, for example, you can choose the eigenbasis of mm, you can choose a basis of eigenfunctions of the second derivative, even for this boundary condition, and to use it to solve this wave equation. So, yes. We saw this example that we can perform Fourier transform for uh, zero boundary for directly on Neumann boundary conditions, uh, but we can also do this for such mixed boundary conditions. It will be on the same Fourier transform, but conditions on this functions will be non-trivial because of this boundary conditions. And actually, it is not very nice because these conditions are a bit transcendental, but at least we know that this works. So, mm, and so remarks that there is a local conservation of energy. Uh, so if we introduce the quantity 1/2 of ut squared plus ux squared, and another quantity, actually I don't know how to call it, let's call it s, which is minus ut ux. We see that d t of e plus dx of s equals to 0, which tells us that well, we can check that if we integrate this equation from a to b, dt of energy and energy density, it will equal to minus s of b plus s of a, and the meaning is that this is this quantity is full of energy. And what is written here is that uh, the energy inside in the interval from A to B is decreased by the flow of energy at the right boundary and increased by the flow of energy through the left boundary. Yes, so it is this is for a one-dimensional wave equation, and if you go to higher dimensions, there are more integrals of motion. There are also conserved momenta, not only energy, and there will be flows of those momenta as well. So, and another remark for higher dimension. Higher dimension. So in higher dimensions, our heat equation has the form uh, like G mu d mu of U equals to 0. Uh, and there is a so-called energy momentum tensor. Which is given by let me remember. Hmm?
Is the matrix which is with the signature -1, 1, 1, 1.
Maybe a 1 minus 1 uh, and so on. But it does not matter actually. It does not depend on signature because everything is kind of covariant. So this energy momentum tensor is defined by, in this case, T mu is defined as U d mu U d nu U minus G mu nu G rho sigma d rho U d sigma U. Like this. Uh, and we can check the following equation that d d mu t mu nu equals to what? It will equal to d mu u d nu u plus
One question about notation. The G rho sigma with the high indices is the inverse or the conjugate transpose?
just inverse.
Or low indices. So
Just inverse g mu g mu rho means delta nu rho. So d mu u d nu u and now we need to differentiate this other part. This is g mu nu d mu d rho u d rho u minus so just this.
Sorry,
Hmm?
should we expect another indices at the beginning?
No, it's the same index. It means summation in mu. It is like this expression.
Okay.
So it's a divergence in this first index.
Okay.
So mm, so if we now look at this expression, we see what that this term written here is zero due to the equation of motion. Like the equation of motion, which means precisely that d mu, it's a D'Alembert operator. Uh, uh, it is zero due to the equation of motion. And if we look at this term, which says that there is a second derivative of u, uh, uh, multiplied in one index by first derivative of u. And this term is precisely the same. It is a second derivative of u multiplied in one index with the first derivative of u. So these two terms actually coincide. So they are so so it equals to zero. And yes,
The first why G rho sigma vanishes. There's no more
which
the G and U
uh,
from the definition to when we derive.
from the equation of motion.
No, that's from the second part.
Ah,
G U B defines G rho sigma. One of them vanishes after we derive.
which one? No, these two terms equal.
Yeah, the constant one. Because we have before the parentheses G mu nu
Yes.
times G rho sigma.
But I just used this rho sigma to raise this upper index sigma.
So that comes from the delta.
Uh, No, it is just definition that d rho u equals to g rho sigma d sigma u. It's just a simplified notation. Hmm. Uh, so so and as a consequence of this, we can do the same. If we write it in the components, we see that d zero uh, maybe we can raise this indices like we can write it as d mu t mu nu equals to zero, or equivalently, we can write that d t like d zero t zero nu plus sum from I equals to 1 to d d i's t I nu equal to 0 di. So um, so it means that it can be written as t zero nu dot plus divergence of some uh, flow with index new. Let us call this uh, as si new. So this equation is also an equation of uh, local equation of conservation of some charge. And if we have this, then we see that integral over the uh, over coordinates or some domain in the coordinate space dx of t0 new dt of such objects equal to 0. So is it fine? Mhm. The integral of the second term because mm, the integral of this second term as nu over dx over d equals to the integral over the boundary, only over the boundary, as nu times uh, times d, and we impose such boundary condition that this vanishes. So it is either something at infinity, or we just ask everything to vanish at the boundary, like in this case. So it should be 0. Hmm.
When we pass from the mu high index to the long index, we have the mu, t, mu, no, which are the indexes about, sorry, over d.
Mm-hmm.
We have t, mu, no,
Yeah.
those indexes, but I cannot read
The mu of t mu nu.
mu.
It is just more convenient to write it this way because lower derivative is just derivative in d over dx, and upper derivative is some is the zero derivative multiplied by a metric. Mm. Mm. So yeah, the consequence is that this wave equation can be considered as such mechanical system which has integrals of motion. So, mm, and interpretation of the components of energy momentum tensor are so 0, 0 component is the energy density, and 0 n components are momentum density. So uh, so and maybe the last remark or not remark. So uh, both so it's called list action principle. Uh, this principle states that both this wave equation or Laplace equation, depending on the signature of a metric, come from the equation. So d mu nu d mu u d d nu u. Oh, no, what am I doing? Like, the mu u equals to 0 uh, can be obtained from the statement that variation of the following functional ds of u equals to 0 for s of u equals to the integral of 1/2 so d plus 1 x d mu u d mu u. Well, the definition of this variation is the following. So maybe that for any function phi in maybe C1 or on RD plus 1, it should be enough. D over the epsilon s of u plus epsilon phi at psilon equals to 0 equals to 0. And so is the definition clear?
Sorry.
Hmm?
Will there be exercises where we are asked to differentiate tensors? Because actually I'm not able to work with this notation. I've never seen it in any course. So.
Well, I didn't know if so. Notation is simple, but when we have u mu, some v mu, it means sum of u mu v mu from mu equals to 0 to d. This is one notation. Another notation is that u mu equals to g mu nu u nu, and vice versa. Mu equals to G mu nu V nu. So it's for lower and rising indices. And also d mu of u equals to du u over dx mu. So all coordinates have upper indices. So
So the first equation that we wrote, so the mu u equals to 0 is a way to represent the Laplacian VI segmentation.
either Laplacian or D'Alembert operator. So it can be, it is equivalent to writing that maybe, so it is sum over mu g mu nu d2u over dx mu dx nu. Maybe let me better use this explicit notation, but concerning the exercises, I'm not sure that it is.
Laplacian in the case of the signature is all positive, and the case of the signature is
Yes, yes. So. So it is this one, and this equals to 1/2 integral d plus 1x g nu d to u over dx du over dx mu du over dx nu. So this is if we want to avoid this annotation, and now so functional is an object. Functional is a map from a space of functions on RD plus 1 with some conditions which may ask two numbers. So it's functional is a linear function on the space. Oh, no, not linear. Functional is a function on the space of functions. So it's a function on the infinite dimensional space. And this condition that variation of functional equals to 0 is kind of an analog of condition that all derivatives of a function at some point equal to 0. So if we have some other well, so independently on what on a if it is maximum or minimum, this condition that so analog that any derivative of a function is 0 is a condition for extremum. It can be minimum, maximum, or something intermediate. So it is an analog of df of x of some maybe vector a over dai equals 0 for any I. For any I. So which is equivalent to so and this is equivalent to a statement that v that sum of v I df df over d a I of a equals to 0 for any v. So it can be called extremum on the infinite dimensional space. So is it? Hmm? Let us call it S. Uh, so yes, it is kind of a function on some finite dimensional space. And actually, in this case, we can write the same formalism for this discretized versions of our equations. In that case, it will be precisely this situation. We will have some function on the finite dimensional space. It will be also quadratic function, and the condition that equation is satisfied will be equivalent to looking for extremum of this function. So let me check that that's logging on. So yeah.
So just to recap, we are doing this on a generic metric G, and at the start we say that this is true also for Minkowski metric, that is a particular metric, but we are treating it as a general metric, right?
Yes, yes. So this calculation does not know anything about the signature of a metric. So, so is it fine? Like, is definition is fine? So and now let us see what it means in practice. So. So let me maybe erase this. So let us compute a variation of S. So, namely, we need to compute this derivative, d over the epsilon, of the integral of 1/2 d plus 1 x d u plus epsilon phi over dx mu du plus epsilon phi dx nu g mu. Taking this derivative is actually equivalent to expand this as a Taylor series in epsilon. Take the linear term at epsilon equals to 0. So it means to so we can remove this 1/2. Mm. Uh, uh, so we have and we integrate over some domain. So it's for equation written in some domain. Uh, 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 so we will have two terms which remove this 1/2, and the result we will get d phi over dx mu d u over dx nu g mu nu. Well, so uh, uh, we have this expression, and the problem with asking it to vanish for any phi is that here we have not phi, but derivative of phi, so we should get rid of it, and if so if you want to do this, we should integrate by parts. So namely, we should rewrite this expression as dd plus 1x d over dx mu of phi du over dx nu g mu nu. Here there is of course sum of mu nu, and here as well. Yes, of course. Yeah. Because otherwise we would get a Laplace operator that depends. Well, actually, uh, we can make this Gemini x dependent and see what happens. Maybe it's a good place to do this. So let us consider Gemini of x, because it is always easier to modify the least action principle, because it contains only the first derivatives, than to modify second order equations. So this way we can get what is a Laplace operator for arbitrary metric. So, well, not the Laplace operator, but um, uh, but a equation Laplacian of something equals to 0. Uh, Actually, there is some modification of this formula for coordinate dependent metric. In this case, we should also we should write not just dd plus 1x. We should write d plus 1 x times a square root of determinant of g. This is determinant with lower indices. So uh,
This is the definition
of the action for this wave or Laplace equation.
so should put through the determinant level.
Yes.
I was meaning that.
Hmm?
I was meaning that.
Ah, here.
Yeah.
Hmm, here. So, uh, yeah. So it is for coordinate independent G. So I have to add this determinant of G because uh, mm, so by definition this uh, determinant of G is determinant of J mu with lower indices. Not of the inverse matrix. And the reason is that uh, uh, that the subject dx1 dx d plus 1 is multiplied by a Jacobian of a coordinate transformation. So it is multiplied by uh, mm, uh, by determinant of dx over dx prime times dx prime 1 and so on, dx prime d plus 1. And determinant of metric is multiplied by inverse determinants squared. Minus 2. So if you multiply it to such objects, then we get some measure which is coordinate independent. So this is why it is a correct formula. Mm, so mm, Well, and it's actually useful to know because it can be applied not only in the case of some curved space. It is useful even if you work with some other coordinate systems in the flat space. For example, if you have uh, if you have an equation like Laplacian of something equals to 0 or equals to a lambda times something, you can either perform a change of coordinates at the level of Laplace equation, and it contains second derivative, so it's doable. You can change these coordinates in the equation and this Laplacian, for example, in spherical coordinates. But it is much easier to first write the least action principle for this equation, because here there are only first derivatives. You only need to know how to transform a metric, uh, and so. Uh, so here. Hmm? So here we have square root of G, right? Mm. right? What's on the question? So there is another term here. I will write it now. Minus integral d plus 1. Mm. Oh, by the way, if you are already considering this equation, let us consider the equation uh, with some non-trivial right-hand side. Let us add here plus equals to lambda u. Uh, uh, so it equals to lambda u. Uh, so I'm saying that we should add here uh, plus mm, plus lambda u squared. Uh, so uh, sorry, I don't think that it is nice to consider also such modification. So let us add uh, uh, right. Uh, so this will equal to integral over d plus 1 x square root of g uh, times uh, d phi over dx mu g mu nu du over dx nu plus lambda phi u. Mm. So now we dx nu. Now we want to integrate this term by parts, so we will write it as integral d plus 1 x d over dx mu square root of g um, phi mu nu du over dx x nu minus minus the integral maybe start it as plus integral d plus 1 x square root of g uh, times yes, thank you. Mm. And here we have this term. So here we have phi, and here we have this term lambda u minus uh, d, and of course here it means that there is summation over mu and nu minus sum over mu and nu d over dx mu uh, 1 over square root of g d over dx dx mu square root of g g mu nu du over dx nu. So uh, uh, this first term is divergence of all this expression, and here I wrote that phi is a differentiable function on Rd plus 1. But if we live in some domain, we should ask that it is a function of on this domain, and as we see from the first term, we should ask it to vanish at the boundary of this domain. Phi on dd equals to 0. So since this is always so for second order equations, or for these actions which are quadratic in derivatives, or well, for the actions which are functions of first derivatives. So this first term vanishes because it can be computed as the integral for boundary, and and here we see
You said that this is divergence, and so we use the Stokes theorem and
yes.
then integrate the form.
Yes, it was originally integral over some domain D, and now it is integral over boundary of this domain D, some normal vector mu mu of this of this expression. But it is multiple. It contains phi, so it is 0 because phi is 0 at the boundary. Mm. So we are left with this condition that this expression should vanish for any phi with such condition. So this vanishes inside D. So in D we have mm, uh, lambda u equals to uh, 1 over square root of of uh, of this determinant d over dx mu square root of g g mu nu du over dx nu and this operator. So if we did not know about the Laplace operator in curved coordinates, we can say that it is by definition Laplace or D'Alembert operator of U. It is D'Alembertian of U, or Laplacian of U. So and we consider the application of Well, shall we? Mm, no, maybe it will take. Hmm? Yes, yes. And,
What it seems that uh, when we have a singular point of that functional, we
mm,
find again the motion equations.
yes, yes. So the point is that this second order equations, wave equation, uh, Laplace equation, their modification to the right hand side, like Holtz and or Klein-Gordon equation, all of them are a kind of classical, are infinite dimensional classical mechanical systems. So they have this description as extrema of some function on the infinite dimensional space of functions. And as a consequence, this presence of conservation laws is actually a consequence of this description by action, because it is it is a kind of Newton's theorem in the infinite dimensional space. So uh, the systems of classical mechanics. But heat equation is different in the sense because it contains dissipation. So mm, and uh, yes. So. Hmm?
Another question. So when we changed the first equation and we added lambda u squared inside the functional, so
Uh,
yeah,
yeah.
exactly.
Mhm.
We put it there because we knew that we should have arrived at the solution we found, right?
Yes.
So
Yes.
so you showed us that with that choice of uh, modification of the first functional, we arrived at the correct answer.
Yes, yes. So in principle, we can put here some arbitrary function of u, and you see from this computation that a result will be that we'll get a derivative of this function in u in the left-hand side. Mm. Uh, uh, so uh, we will actually use this approach to compute Laplace operator in different coordinate systems. Because, of course, if you have a change of coordinates from a Cartesian system to some other one, you can transform that the second derivatives, but it's easier to transform the least action principle. And it's true also for classical mechanical problems of finite dimensional case, because Newton's law is Newton's law can contain second derivative, and it is hard to change it. But action contains only the first derivatives, uh, and it is much easier to write energy of a system than to work with second Newton's law. Uh, and also, this the presence of this list action principle is sometimes important from the computational point of view, because sometimes it is easier to choose some space of functions and find a minimum on this space than to solve second order equations. So it's one of ways to switch from infinite dimensional problem to finite dimensional one. Mm. And uh, well, uh, actually, uh, mm, uh, I have another remark, but maybe for the next time. Uh, mm, well, the remark is that wave equation in 1 plus 1 dimension is for continuous variables is actually equivalent for the wave equation in the discrete variables, and we can look at this a little bit more careful and understand in some other way why this boundary value problems for the wave equation are bad, and initial value problem is good. Okay, thanks for your attention.